So now let's look at the words continuous and differentiable. That's the next thing. We want to see them because you can be asked about these things on a graph, and you can be asked about these things to test these things using an equation. And those are two separate things, right? So the word continuous versus the word differentiable using the graph. So let's do part C. So we want to see the words continuous and the word differentiable. Okay. Now, the first thing, I'm going to test them using a graph. So the first thing is we are going to test these words using a graph. And let's see how it is, what it is that we look at. So when they say the word continuous and you have a graph, what makes something not be continuous is either the function having a hole, or the function having a jump, or the function having a vertical asymptote. Okay, so when we're using a graph, okay, let's say things that bring discontinuity. Okay, things that bring discontinuity at a point. Discontinuity at a point. At a point, yes. So things that bring discontinuity at a point is if there is a 1 jump, 2 hole, and then 3 is vertical asymptote. So you can put vertical asymptote. I don't want you to make this hard. It's not hard. Come on. So when we say a jump, it's like you have a function like this, and we'll put the function so it's like it goes like that, ends here. Okay, you'll be having it goes like this, and you have a circle here, then there's a dot here, then it continues here as a circle. So this is a jump. This function, when it gets to this x position here, what does it do? It jumps to this point. Then when it wants to continue, it will jump to this and continue. So this is a jump. For a hole, it's like you have a function like this, and then you have a hole in the function, then it continues. We will say this function is not continuous at this point C. This function also is not continuous at this point C. Then again, a vertical asymptote is another thing which brings discontinuity. If you have a vertical asymptote, then your function can go like this, and the other one come like that. Even if it comes like this, then there's going to be discontinuity because of your vertical asymptote. Remember, a vertical asymptote is a vertical line. Now, if you put a horizontal asymptote, does it cause discontinuity? Oh, no, it doesn't. It doesn't necessarily cause that, because you can have something like this. Here is a horizontal asymptote, but it's not making it discontinuous, even if it goes like this as well. This function is continuous, although there is a horizontal asymptote. So horizontal asymptote does not cause discontinuity. It doesn't make it break. It can still continue on and on and on. Because remember, being continuous means you can just draw the whole thing without having to pause or raise your pen. But if these things are there, remember we are talking about a graph, okay? So in part A, it was for continuity. Things that make it not continuous. We have seen them, okay? Things that bring discontinuity at a point. Now, what you must know is in B, you should know that a function, a discontinuous point cannot, cannot be differentiable. So in other words, if there is a discontinuity, it will not be differentiable. If there is no continuity, then there is no differentiability. So if it's not continuous, we can say not continuous is going to lead to not differentiable. Okay? Is going to lead to not differentiable. You must remember that. Please. If something is not continuous, then it's not going to be differentiable. So if we are describing, if you meet this point x equal to c here, at this value of c, then you are going to say at x equal to c, what is there? It is neither, function is, you can say function is neither continuous, nor differentiable. So these are the things that make it not continuous, and if it's not continuous, it can't be differentiable. So it is neither continuous nor differentiable at this point, x equal to c. At x equal to c, not on the whole thing, but exactly at x equal to c, where that thing is there, that is when it's not going to be continuous nor differentiable. Now let's look at the second thing, which is b, and that is just looking at the word differentiable. We want to see the word differentiable, okay? Alone as a standalone. That is for continuous functions, okay? The word differentiable, we are dealing with for continuous functions, because if it's not continuous, we can't even test that word. This is obviously for continuous functions, okay? Because if the function is not continuous, then it cannot be differentiable. So we are now testing differentiability on a continuous function. So let's see because if a function is not continuous, it can't be differentiable. At that point, there's no way it will be. Being differentiable just means that the gradient on the left of the thing on the right is the same as the gradient of the thing on the left, which will never happen if there is a jump or a hole or an asymptote. It will never happen. Now, on the word differentiable, we are looking for at continuous functions. So we are now wanting to see things that make a function, not differentiable. What are the things that make a function not differentiable? What are those things? Okay, number one is a cusp, and then number two is a sharp corner. So a sharp corner, okay, we'll be having a continuous function, but if these things are there, then it won't be differentiable. For cusp, we are talking about what? Things like this. You have something like this in your function here, or you have something like this in your function, then it is not differentiable. Then on the sharp corner, you have something like this. This is again not differentiable. So what word do we use if this like this? This will be continuous because it doesn't have a jump or a hole or an asymptote. Continuous, but it is not differentiable. It is continuous, but it is not differentiable. These are the words we use if there is such a point. You say at x equal to c. The function will be continuous but not differentiable. Where at this point where the cusp is, this is at point C. Let's put it. We can put, I need to put the other thing so that you can see this point clearly. So this is your y and x axis, then this is your point C. Then we can put again y and x axis, then this will be our point C. Then we can put again y and x axis, then this is our point C. So we know at point C, it is continuous but not differentiable. We have sharp and we have cusp and we have sharp corner. So this is what happens. Then now we can deal with part C where we just have differentiable. So when we say differentiable, then we know that obviously it is also continuous. Okay, it is also continuous. The only way it can be differentiable is it must also be continuous. Where is that point? What is that going to be like? And something is differentiable and continuous, it's just something like that. And here where there is no jump, nothing, no cusp, smooth like this, even just a curve like this, here you'll be having a nice continuity. That is what we will be having. So this is going to be, we just say it is differentiable. But remember, it also means it is continuous. So this word differentiable only exists for continuous functions. If it is differentiable everywhere, okay? This thing is differentiable in its entire domain. So in its entire domain, that means the whole thing is differentiable. So there we go. That is the whole thing. So it's like, let's say it starts at -1 and ends at 5. So it's like d from -1 less than or equal to x less than 5. Right, that is going to be it, and you are done. So remember, these are the words to use, and remember, you'll be looking at a point and you'll be looking for something. So this is where it is not going to be differentiable at x equal to c, but everywhere else it is going to be differentiable. But where there is the corner or the cusp, it won't be. How good is that? It's good, huh? Now, the last thing is then how do you see this when you use equations? We've seen how to use a graph to do it. When you use equations, we can now say using equations, So we are now doing using equations. We want to test the word continuity and the word differentiability. So here you can now say for example, you have a function f of x, okay, being equal to, let me look for a function here. And here is an example, like we start with continuity. Here it says, for what value of b is this continuous at every x? So it can ask you like this, or it can ask you as to say, let's remove this. Let me look for the other one. It can ask you again to say, is the function continuous at this value? But here they are saying, for what value is the function continuous? Now, you can just say at every x. Now, if there is a situation like this, so you should always know that we test continuity at a certain point. So for this to be continuous at every point, there has to be a certain point we use though to test continuity. And if there is continuity at that point we know it will be, there'll be continuity everywhere. And the point is here, where these two pieces of the graph meet. They're going to meet at x equal to -2, here at -2. So that means here we are going to be testing continuity at x equal to -2. Now, continuity for an equation, continuity has an equation, and we call it the continuity equation. The continuity equation always looks at what you are testing. Where is the continuity? We are testing continuity at x equal to -2. So what is the continuity equation going to say now? Your function is a g of x. So it's going to be g of -2 is going to be the limit as x approaches -2 of g of x. If these are equal, then your function is going to be continuous at x equal to -2. So for continuity at x equal to -2, what? G of -2 must be equal to the limit as x approaches -2 of g of x. Okay? So what about here? Continuous at every x. We're going to say again, here it's an f of x. So where is the controversial point that we are going to test continuity? Well, for here they are meeting at -1 and these two are meeting at 1. So we do for both. We're going to do continuity equation at 1. So we will say we'll test for both, and you see how we'll do it piece by piece. But first you should know the continuity equation. So we'll say for continuity at x equal to -1, now we'll be now saying f of -1 is going to be equal to the limit as x approaches -1 of f of x. Okay, it's all on -1. So we'll end up we'll get f of -1. Then we'll get the limit as x approaches -1. We know that as x approaches -1 is a two-sided, but these are piecewise, so we do one side at a time. So we'll say -1 from the left, then we'll say -1 from the right, then we'll combine. Here we'll again say, what about the other point? For continuity at x equal to 1, we'll now say f of 1 is going to be equal to the limit as x approaches 1 of f of x. That is what happens. F of 1 is going to the limit as x approaches 1 of f of x. That is how we are going to be testing continuity. And we're going to solve the limit, this f of 1, we get it. Then we'll solve this limit. We'll come from the left, we'll come from the right. And when we have them, we're going to make those things equal. Then we are going to check. So this continuity equation has three things you must know that. Number one, this f of 1 should be existing. For continuity to be there, f of 1 should be it should be defined. Okay, it should be defined. It should not be undefined. It becomes undefined if f of 1 is in a fraction and it gives us a denominator of 0. That's undefined, so that means f of 1 is not there. So, but if it gives us any other answer, that means it's there. So f of 1 should exist. Then this limit should exist, and for this limit to exist, we know the limit from the left should be equal to the limit from the right. So you're going to test the limit from the left, you get the limit from the right. They're going to be equal to each other. If they are, then the limit exists. So now you have the limit and you have f of 1, and now these two should be also equal to each other. That's the third thing you are going to test. So f1 should be defined. Then the limit as x approaches 1 must exist. Then they must be equal to each other. Then you would have proved your continuity equation, right? So continuity equation is like that. Then from there, we now talk about the equation for testing differentiability, but this is the continuity equation. I'm sure you kind of see what it works and how it works. Now we'll do for the one for differentiability. We'll do it in the next video. Goodbye for now.